Hello, Team Physics C. I'm testing out my new side-by-side annotation setup, which, by the way, you are welcome to use for your test corrections videos. Um, it's just in the back of the lab. I just wanted to provide a quick sort of overview, kind of like an executive summary of the class notes on simple harmonic motion, just because there's a lot of tiny detail that you can get lost in. So I just want to make sure that we have a good sense of the theme. So I'm going to work on this piece of paper here, and you can ignore my face on the other side. So basically, the way I want you to think about all simple harmonic motion is that we look to find evidence that this is true when we write Newton's second law for the system. That often will also be something that we look for in the rotational form. Why are we looking at this for simple harmonic motion? Well, that comes from the kinematics. In other words, back in the day when we said, hey, if something is oscillating back and forth as a cosine function, if you differentiate that twice, you see that the original function comes back with a negative sign and then with this multiplier. So if, and you, as you can see, this is x of t. So in general, if we can find that this and this are on opposite sides of the equation, we'll say that we have a natural frequency of omega squared. Okay, so we looked at a bunch of different cases where this was true. So let's just kind of try and make sense of what they were and what the common things are and what the different things are. So the first was the mass on spring. Okay, so the mass on spring was essentially when we said we have a horizontal oscillator without friction, and when we displace this from equilibrium back and forth, we draw the free body diagram and write Newton's second law for straight line motion, we see that. So this pretty straightforwardly gives us that. And then there were two interesting things here. One was, what's the story with the effective mass? Well, I'm going to refer you back to your notes for that. And then the other was this damping. In other words, if you have a term that is a velocity dependent dissipative force, you can show that the x of t function is what we would expect for an oscillator multiplied by a decaying exponential, where the decaying exponential decreases the amplitude like such. So it's a little bit like I think I said in class the other day, what you get when you take a sinusoid and you multiply it by an e to the minus t function, you get something like that. Okay, so that's the mass on the spring. The other big sort of set of ideas in this unit was the physical pendulum. Now, the physical pendulum we treated with a torque problem. So the torque problem went something like, you have your squash of physics, and you've got a pivot like that. And then if you give this guy a little nudge of theta away from equilibrium, that the component of gravity that is exerting a torque, in other words, the component of gravity that is perpendicular to the moment arm h, is behaving as a restoring torque, because as you get farther and farther away from equilibrium on either side, this restoring torque will tend to get bigger as the displacement gets bigger and it's pointing back towards equilibrium. So we said for the physical pendulum that the sum of the torques was I alpha. We then said that the torque here was hmg sine theta, or as you know, rf. And then for this, we wanted to be sure that we were talking about the moment about the pivot. Okay, and that's because if the center of mass is here, um, obviously if you remember our parallel axis theorem, we just want to be sure that we understand that the moment of inertia about the center of mass is one thing, but then there's this moment of inertia about where the object is anchored. Okay, small angle approximation here, that's something that we'll discuss more in lab next week. We need a minus sign because this is restoring. HMG I pivot alpha times theta. So that sine theta becomes theta with my small angle approximation. So by inspection, we have simple harmonic motion. We have alpha of t is equal to theta of t times the negative of a thing that will be related to the natural frequency. So for our system, that's HMG over I pivot. Okay. This would predict that the period is 2 pi. Sorry about that. This would predict that the period of all physical pendulums is 2 pi times the square root of I pivot over HMG. Now, that formula, it seems kind of straightforward, and it sort of is. It comes from this generalized treatment of the physical pendulum, and this is the starting point for literally every problem that we're going to do in the lab, and then also the Wiley. So the cases that we looked at in class were the physical pendulum that is the uniform rod. Now you should be able to very quickly and easily show that that's equal to 2 pi times the square root of 2L over 3G. And then for the mass on string, this is called the simple pendulum. It's 2 pi times the square root of L over G. Now we looked at this really nice demo where, if I had a string and then I had a rod, the question was, like, how long is the string such that these two have the same period? It is not the center of mass. Okay, actually, it is at 2/3, right? So if we wanted to have our string have the same period as our uniform rod, it would be that long, and we showed that kind of with a simple demo in class of letting these two things wiggle back and forth side by side. We also were a little interested in the idea that that was the center of percussion, although we're not going to make a big deal out of that. The other thing that we looked at was the torsional oscillator, or the torsional pendulum. And this was sort of a unique little application of the this is sort of a unique little application of the whole second law argument, because we don't even care about where the how to treat the torques as forces. If you go back to your notes, you'll see that we just talked about angular displacements and then something called the torsional constant. But the reason why we stopped to talk about that is because it's a nice way to measure moment of inertia. Okay. Finally, and this is going to be the topic of, and then I'll be done in a second, but this is the topic for next week. We're going to take a careful look at how the equation 2 pi root I pivot over HMG, we're going to take a careful look at how this varies for a uniform rod with a bunch of different pivot possibilities. So, we might have there, we might have there, and so on, down to the center of mass. And so the question is, if the period, if you do the math, right, and we define this distance as h, you can see that as h goes from 0, right, so h is defined as the distance between the center of mass and the pivot location. So if h is 0, the period is infinite. And then if h goes to L over 2, the period becomes what we would expect for this previous example, 2 pi root 2L over 3G. So I guess the question is, how does it behave in between? And if we plot that polynomial, so the polynomial specifically for a rod of length L and mass M would basically look like this: 2 pi times the square root of 1/12 ml squared plus mh squared. I'm just writing explicitly the moment of inertia about the pivot over hmg. And I guess the idea here would be that if you plot that, you see a min, and then you see an asymptote as we go to, so this is a weird axis because actually here's h equals 0, and then here's h equal L over 2. So it's really plotting to the left. Let's not let that bother us though. There's a min here, and that min you can solve for analytically by differentiating this with respect to h and finding the 0. So that's going to be the subject of our lab. We'll take a photo gate. So we'll shine a little infrared LED through this. We're going to give you an acrylic board, and you'll have like a little stopper on it. And the timing for the period of oscillation is going to be like millisecond or tenth of a millisecond precision. And you'll be able to actually discern the presence of a min here. And then you'll be able to say that it gets higher like that. So now this experiment doesn't have a lot of practical application, but it does really nicely show you that the differentiation to find a min has, like a very clear application in this particular physical system. Okay, so that's sort of an overview. I hope this helps you wrap your mind around the sort of lots and lots of notes that we did the other day. See you next week.